Get that in the. I mean, you can. What's up?
Yeah, I got a question.
Yeah, because it would be. It is only two possible outcomes. If that's the case. If they are two possible outcomes. So I don't know.
There's
There's only one.
There's only a single answer. I don't know how you come up with two.
Okay, so repeat what you have said before, so when you have made the comment.
I said, if you don't see anything there, what is it that you're integrating? One.
Oh, okay. That's what you can-
Yep, understand. It's recharged. I got 1 minute left. Oh, where'd you do your rewrite? Oh, you just erased it versus. Okay, sorry, I didn't make the clear one on the newspaper. Just did a rewrite. Is it? Cool. All right. No, it's all good. All right, 30 seconds. Screen, stop share here. All right, locking answers here in 5. Actually, let me write it down first. What are the bounds? What was it? -2. -2201. All right. Locking answers in 5, 4, 3, 2, and 1. So locked. Yep. Make this back full screen. Lock it. What's the answer? Four sounds right. So, what shape are you essentially making? You're just making a shape. Remember, these double integrals are always just volumes, right? It's just a 3D shape. Where are you balancing the x and y axis? The -2 and 2 on which axis? X. We go from -2 to 2. What am I changing on the y-axis? 1. Which means that side length of 4, I have a side length of 1. And then this shape has a height. What is the height of this shape? Constant value. Height. What shape is this making in 3 dimensions? Not a cube, because it's not even, but rectangular prism, right? Just a small remembering, how do you find the volume of rectangular prism? Times height. So yeah, it should be 4, but we can do this through integration. Okay. So integration says first, integrate that inner interval. 2 the x, and then whenever I figure out whatever that is, I integrate with respect to y. Well, what's the antiderivative of 1 with respect to x? X, which means this is 0, 1 of x evaluated from -2 to 2. Guessing based on that noise, some people probably overcomplicated this. All right, well, I evaluate x from -2 to 2. It means I plug in a 2, subtract by plugging in a -2. Going to give me the total value of 4. And then when I integrate 4 with respect to y, what do I get? 4y, and this is being evaluated from 0 to 1. Just 4. So really all I was looking for here was making sure that you remember how to do the nested integration. Trying to make sure at least give you a nice little easy integration. Try to get that all on one page. There we go. So, what questions do you have for me? Where did I put my notes? There we are. All right. Hearing none. Another example, but one with a little bit more complicated integration steps to it. So, let's determine the volume of shape created by the function fxy being e to the 2x plus 2y. Over region R, which we're going to say is 0 to 4 and -1 to 2. So I have to set up my integration. That's the first big step. All right, which one do you want to integrate first, with respect to x or with respect to y? What was that, Malvern? Sorry? Yeah, it doesn't matter. We can do x first. That's why I'm asking y'all, because really, you can do it either way. Good afternoon, Simeon. So this integral over this region R for my function, I'm choosing to do x first. and then y, which means the bounds for that integration need to be from what to what? Four. Got it. And then what about the outer integration? Needs to be from what to what? Negative 1 to 2. So I now have it set up. And the way I deal with double integrals is I view them as nested. So I have to do that inner integration first. So I have integral from negative 1 to 2. But I'm actually with that integrating integral from 0 to 4 of e to the 2x plus 2y. With respect to x, figure out whatever that is, then integrate with respect to y. All right, well, I have to do that integration. Right, you got other stuff surrounding it, but I can just zone in on that integration with respect to x. Can anyone tell me what that integral will be just from looking at it? Do you know what it is? So we will see itself repeat. But there's something else with it. So remember, we're integrating with respect to x. So y is what? Constant. Since the 2 times y is just a constant value. So think about how we normally do differentiation with e to the x, right? We multiply by the derivative of whatever's in the numerator. The antiderivative or integration, instead of multiply, we divide. Right? We kind of do the opposite. So if I took the derivative of 2x plus 2y with respect to x, what would it be? Just be 2. Right? Because y is constant, x is my variable. Derivative of 2 times x would be 2, derivative of 2y would be 0. So I need to divide by 2. Now, the way I wrote it, I didn't really give myself plenty of room to write division by 2. So how can I rewrite division by 2? Multiplication by a half. And I evaluate this from 0 to 4. How are we feeling with that? Come on now, we should feel more comfortable with these integrations. I'm going to go the long route. Here's an integration technique that'll probably make this a little bit easier. My integration by parts. Do substitution. So I'm going to take that exponent. Substitute it for u. Right? That's what my exponent is. So then I say, all right, what happens if I take the derivative with respect to x? Well, then du will be 2 times the derivative of x. Which means that dx is equal to du over 2 or 1/2 du. Replace that 2x plus 4 with my u, and replace my dx with its equivalent with du. Now that's a constant multiple of 1/2. And what do I do with that constant multiple of 1/2? Pull it out front, right? I can pull constant multiples always out in front of the integration. Which means this is 1/2. Antiderivative, that doesn't look like the u, looks more like the 4 there. Antiderivative of e to the u with respect to u. What's the antiderivative of e to the u? It's e to the u itself. It's its own derivative and its own antiderivative. Now I replace that 4 with a 2y. What changes? Not much. Because when we're integrating with respect to x, we always consider y to be 1. Just like that 4. Does that get this back? Cool. So I now have to evaluate e to the 2x plus 2y times 1/2 from 0 to 4. And that's again with this respect to this variable x. The only thing I'm doing is replacing x with the bounds 4 and the bound 0. So I'm going to have e, we pull that 1/2 up front, 1/2 e to the 2 times 4 plus 2y minus 1/2 e to the 2 times 0 plus 2y, and then integrate with respect to 1. Now I'm going to want to clean that up a little bit before I actually do the integration. Both of those two terms, without even evaluating or doing any of the arithmetic in the exponents, they both have a common factor of what? 1/2. So what can I do that factor of 1/2? Without front of the integration, in front of the integration. And now let's figure out what these exponents are going to look like. Well, I have a 2 times the 4, which gives me what? 8. And then I have a plus of 2y, so that first exponential term is just going to reduce to e to the 2y plus 8. What about that second exponential term? Just 2y. That 2 times 0 is 0, just goes away, leaving me e to the 2y dy. So now I need to integrate these. Try to do them quickly. Let's first start with maybe the easier one, which is e to the 2y. Well, it's antiderivative. What's that? Oh, sorry, you're all saying too. I heard Balmer say something first. I just couldn't understand it.
No,
E to the 2y. Yeah. Okay, what Kyle was also saying. What about the antiderivative of e to the 2y plus 8? Thing. Well, technically not the same thing exactly, include that plus 8, but what you're saying is kind of like the same form for the antiderivative, i.e. kind of putting that 1/2 out in front, and in that, yes, you are correct. So I need to evaluate this with my y's being at 2, and then subtracting it with my y's being at -1. Now I can simplify this down a little bit, because if I leave it as is, it's going to give me a nice long expression. What do both these terms inside that evaluation have in common? 1/2. So what can I pull out? 1/2. And I multiply it by this 1/2 I already have out here, it turns into a 1. 4. Whether or not you think that is actually simplifying it down, fine, I think whatever, just this way my brain works. Not really too much I could do. I could pull out e to the 2y if I wanted to. That's not really going to improve it too much, in my opinion, so let's just plug it in. So I replace my y's with a 2. E to the 2 times 2 plus 8 minus e to the 2 times 2 And I'm going to subtract from it when I plug in -1. E to the 2 times -1 plus 8 minus e to the 2 times -1. Simplify all these exponents. Make it e to the 12 minus e to the 4th minus e to the 6 plus e squared. Can't really combine any of those e's because they all have different exponents. This is my final answer. So, what questions do you have for me? So if you're feeling rusty with some of these integration stuff, easy answer is to say, go back and look at your, what is it, OpenStax Volume 2, where you go through pretty much all of your stuff, where you can see all the stuff that you cover in calculus, doing a lot of explanations. Okay. However, Appendix A of our textbook has a nice big old table of all your integrations. So if you've forgotten something like this, integration of 1 over y with respect to y, which hopefully after differential equations, that's probably fresh in your head now, right? But if you did forget how to do it, you can go to that table and say, oh, that's the right form I have, this is what the answer is. Right? So make sure you go look at that if you need a refresher. Because from here on out, I'm assuming that you know how to do these integrations. All right, so with these double integrals, we're making a very, very nice assumption about the region that we're integrating with. Right? The region that we're integrating over is always some nice little rectangle. My question for you is, do you think that's always what our regions, integrating regions, are going to have to be? You can think of just like a sphere, for example, in 3 dimensions, right? You technically learn how to find the volume of a sphere in calculus 2. But if I look at that as a region, even if I look at it from above, it's just going to form a circle. Oops. So what if instead this was my region? Question is, how am I going to figure out how to set up my integration? It doesn't even have to be a nice little shape like this. It could be something more complicated. Okay, so the question is, how do we integrate over a more general region? Now, we're going to generalize it, but we are going to keep it to kind of 2 simpler scenarios. And if you're wanting to follow along with the textbook online, this is section 5.2. So think back to these. This XY plane is just my domain. It's where I'm pulling all of my function values whenever I'm trying to do these integrals. Now the height is determined by some function that's given. What I have to determine is what was the region I was going, which was nice for a rectangle, right? I figure it out. Easy change in x, a nice little constant change in x, and a nice little constant change in y. Now that idea of how I change across the x-axis and how I change across the y-axis is still going to be the same. It's just not going to be a constant function. I need to say, okay, is there a way I can define a function for these boundary edges? Well, whatever that function is then going to determine what my height is. Because if I'm considering along the x-axis, the height of my region changes, or my change in my y changes as I travel right along the x-axis. They get larger, stay about the same, and smaller. And if I did a similar image along the y-axis, all my changes in x's would be different as I travel up the y-axis. But one of the things that we have in mathematics is we have functions that can describe change. So all that's going to happen is when I set up my integration, my bounds aren't going to be nice constant numbers. All I need to do is figure out functions that are going to define the bounds of this region of my integration, and those functions are going to go into the bounds for my integrals. So instead of having double integrals with constant lower limits and upper limits, now we're going to introduce functions into those integrations as well. Now, when we do that, we're going to just start with two different types of regions. And that's really all we're going to stick with. You can get to some more complicated stuff, but really that's outside the purview of what we want to cover in this course. So first up, definition. So to get away from R for rectangle, like we've been doing before, we're going to just do a capital D for our region instead. But it's still talking about the region that we're integrating. So region D in the XY plane. Is of type 1. If it lies between two vertical lines and two functions of x. Two. So in generalizing, what we're essentially saying is just, okay, well, with rectangular regions, we had fixed vertical lines that made up my rectangle. Now we're going to say, okay, we're going to keep two of those vertical lines, but the other pair of vertical lines from this rectangle are going to change depending on where you're at on the x-axis. So visually, yeah, I guess green. This could be my region D. I have those two vertical lines that are making up the edge of my region. And then I have two functions that are defining that curve. And the y values of this region are always going to be somewhere between whatever this line is between g1 of x and g2 of x. Doesn't have to just look like that. This would be a more complicated function because it's a piecewise function. So all I'm doing is I'm fixing vertical lines on my x-axis, and then where my y values are at in this region change depending on where you're at. So this is what it means to just be a type 1 region. There's only two types, type 1 and type 2. What do you think changes for a type 2 intuitively? Yeah, so I'm going to I'm no longer going to be fixed on the x-axis. What axis am I going to be fixed on? The y-axis, and I'm going to be changing with respect to x values. Yes. Oops, I don't need a capital R there. So region D in the xy plane is of type 2. If it lies between two horizontal lines. And two functions, h1 of y and h2 of y. Two horizontal lines are essentially saying vertical lines with respect to the y-axis. Usually, since we like to keep the y-axis vertical and x is horizontal, we're saying there's two horizontal lines there. And your images for this look something like the following. Whoops. Wrong way. So this right here is an example visually of what a region of type 2 looks like, right? How I change along the x-axis depends upon where I'm at on the y-axis. However, I know I'm always between these two horizontal lines. First one being, or the higher one, y equals d. Lower one, y equals c. And be a little more careful to make sure these are horizontal. You can make a nice little bowl-like shape. Again, where this vertical line on top, I'm sorry, I said vertical, horizontal. Ugh, that's a big distinction. That horizontal line on top is a constant function with respect to y. You have your horizontal line on bottom, which is a constant function with respect to c. And then you have two curves. They're also giving your lower and upper limits on your x-axis. So our integrations are going to depend on making sure we can identify type 1 or type 2. And here's the key. In most cases that we're going to consider, you can do it as either or. What we're going to find out is similar to what we were talking about with which way I do integration first, whether I do integration with respect to x or with respect to y first. That ends up making the integrations I have to do easier. Same thing with choosing the type of domain I wish to consider this as. If I consider it as a type 1 versus a type 2 might lead to an easier or harder integration to do later on. But the first skill I want us to see is just making sure we can identify what the type 1 region looks like and what a type 2 region looks like, given some information. So, but really quickly while we're here, are there any questions? All right. We just work with some more. So I want us to consider the region in the first quadrant. Between the functions y equals square root of x and y equals x cubed. We're going to describe this region as both a type 1 region and a type 2 region. I guess I already said region before, so it's being repetitive. So just describe the region as type 1 and type 2. What do you think is going to be very helpful? Absolutely. But before I even go finding vertical or horizontal lines, can anyone picture what this is in their head, what this region looks like in your head? Well, let's draw a sketch, right? It doesn't have to be an exact picture, but at least sketch out these two functions so I can see this region. And once I have this region, then I can use that to help guide me on finding those vertical and horizontal lines. That's great. Maybe let's see if I can get it here. So I'm only worrying about first quadrants. And I have to say, okay, well, If this is my y-axis and this is my x-axis, what does the square root of x function look? What was that? Yeah, kind of a half parabola if you're looking in the y direction. All right, so it goes up pretty quickly after 0, but then after 1, it starts to level off. All right, again, I'm just sketching it. I'm not trying to be exact. Being exact might be helpful later on, but really our point right now is just to get an image of this thing, get an image of this region. Now, the other graph I have is y equals x cubed. So in this case, y equals x cubed, we know goes up, right? Because as I start cubing numbers, they get extremely large. But think close to 0, right? What happens if I cube 1/2? What does it become? So 1 over, yeah, 8. You're good. 1 over 8. So it becomes small. And it only ever starts getting larger once I pass 1. So I start off being slow, and then after some point, I'm going to start increasing pretty rapidly. And I know that these two graphs are going to intersect. So we're talking about the region in the first quadrant between these two functions. What we're considering is that region right there. That is the region of consideration. So now I have to say, all right, I need to figure out on the x-axis what values do I lie between? I'm going to keep that, but well, where do these two functions intersect at? That's a good question. Because wherever these two functions intersect at, that's going to give me the farthest left of this region on the x-axis and the farthest right of this region on the x-axis, giving me that my a value is somewhere in there, and my b value is somewhere here. And then anywhere between that a and b value, how wide this thing is then determined. I'm going to use spread. That's going to show up a little bit more. How wide that region is, essentially how far I need to go on the y-axis, is then determined by the difference being between those two functions. So the key here is I need to figure out what a and b are. Figure out what I'm bounded between for on the x-axis, giving me a type 1 integral, or I said integral. Type 1 domain, which will lead to a type 1 integral. So I'm going to be fixing myself between two vertical lines on the x-axis, i.e. where that a and b are. So I need to figure out when does the square root of x equal x cubed? Now you can do this intuitively or you can do this algebraically. What are the x values that are going to make that true? 0 is definitely going to be one of them. If I take the square root of 0 at 0, and if I cube 0 at 0, and 1. Square root of 1 is 1, and 1 cubed is 1. Now, if you weren't able to get that intuitively, let's scroll. Oh no, you froze again. Well, I can turn this into an equation equal to 0. Yeah, factor out, but here I can't just factor out x, right? But I can factor out a square root of x. Giving me that the square root of x times x to the 5 halves minus 1's got to be equal to 0. And we know from algebra, this is only ever true when the square root of x is equal to 0 or x to the 5 halves minus 1 is equal to 0. Well, that first equation then tells me x has got to be equal to what? 0, right? Like we intuited. That second equation says then, well, 1's got to be equal to x to the 5 halves. Well, I raise everything to the 2/5 power. And that's just going to give me x has got to be 1. Because 1 to any power is always going to be 1. So I now know, okay, on the x-axis, what I'm bounded between. So my region for the type 1 is going to be all points x and y such that, well, I know my x values are going to have to range between 0 and 1. What about my y values? What are they going to range between? Well, I know what the curves are that are defining it. Can't fit it all on one page because that break. We're going to make it a little smaller. That way we can see everything. Okay, where I'm going along this x-axis, which of these two curves is making my lower y values? X cubed, right? That's always going to be the bottom boundary for any of my y values. What is the upper boundary for any of my y values? Square root of x. So my y values are always going to be greater than 1. X cubed, that lower bound. And they're always going to be less than my upper bound, which was x. Actually drew these for type 2. All right, and the next question is, how big can I make it? It's not great readability. Let's see if I can manage with this. Type 2 is a little different. See if I can fit it up on the same page. In type 2, I'm considering my y values being fixed between 2 points. And then my x values are changing based on some functions of y. So those functions of y, again, are just coming from the curves. So I have to look at these two curves and say, all right, well, they're currently functions of x. If I'm going to write this as a type 2 domain and I want them as functions of y, I need to rewrite them. So I know y is equal to the square root of x, and y equals x cubed. And if I wanted to rewrite these equations so that x is my dependent variable and y is my independent variable, well, I need to have x is equal to something on both of them. Well, if we work with this first equation, y is equal to square root of x, what do I get? Y squared, square both sides. If I want to get rid of that cube on the x, and take the cube root. Now, if I hadn't done all this work with type 1, type 2, I wouldn't know that at least the x values for that region. Right? That A was 0, B was 1, which means I can also get the y values. C would be 0. And what would my D value be? Well, we'll just plug 1 into either function as x. What is the square root of 1? 1. I'm seeing the time, which is why I'm trying to talk quickly through this. So I know my y values are going to be ranging between 0 and 1. Now the question is, my x values. Well, my x values are going to be still between these two curves, but I have to tilt my head to the side and think of the y now as my horizontal, x is vertical. And I say, okay, of these two curves, if I'm traveling in this direction, which is the first one I'm going to come across? This line right here. Now it's a function. If the function of x is square root of x, but I changed it into y squared. So the lower bound is this function that's created by either y is equal to square root of x, or what I need, x is equal to y squared. So my x values are always going to be greater than whatever y squared is. And then I keep traveling. I get to the second line, and this is my upper bound. It was the function y equals x cubed, but we rewrote that as a function of y to be x is equal to cube root of y. That's what my domain is going to look like as a type 2. Both ways of talking about the same region, just two different perspectives. Do I fix constant values on the y-axis, or do I fix constant values on the x-axis? Definitely going to stop there because I'm well over time than what I'm used to. But all of our integration that we do for integration over a general region, we have to play this game every single time. Because without realizing what our region is and what our x and y values are bounded between, we can't even set up our integration. So we're going to do more of this on Monday. See, we have 5 minutes till Diffie Q. So let me increase this. Any questions for me? All right. So we only have 5 minutes for Diffie Q, but I guess, hey, Diffie Q is only until 2:50 today, right? Not 3:15. Use the 5 minutes as your break. We'll come back here in a second.